The next thing is the effect of zeros. Let's start with still second order system. This one we now know how the response will look like. What if we have G tilde S? That is this. It has 1, 0 located at location of S equal to negative alpha. For this one, the step response, let's do this. So let's suppose the original step response to this one is Y of S is G of S, U of S. And then the response for this one is Y tilde S is tilde S, U S, and it equals to S plus alpha, the extra term, times Y of S. This is mathematically how these two signals are related. We know how Y, for the first system, how it looks like. Let's see. Is this system underdamped, overdamped, or critically damped system? So you can check the damping ratio, right? For this system, omega n squared is 2. 2 zeta omega n is 2. These two coefficients. So that means omega n is square root of 2. And zeta is 1 over omega n. So it's 1 over square root of 2. So it's less than 1. This is an underdamped system. So Y roughly looks like this. And you can calculate the final value and have a more accurate plot. But this is how Y looks like. Now for Y tilde, let's see what's going to change. So Y tilde is Sy of S plus alpha Y of S. And that means in the time domain, Y tilde t, after applying inverse Laplace, it will be inverse Laplace of S times Y of S. That is Y dot. Right? And the inverse Laplace transform of alpha times Y of S is alpha Y of t. So that's mathematically how the two signals are related. If you add a 0, then the response will be, the 0 will, one component will scale the response. And another component is this adding this derivative of Y into the picture. So let's see. Let's try to draw. I will draw on a separate plot. All right. So the scaling effect. Let's say it's something like this. That's just scales the shape. So it's going to be the scaled shape plus a. Let's try to visualize how the derivative of this will look like. So the derivative of this is initially the slope is positive, right? It's going up. So initially this value is positive. Let me actually try to draw it in this way. This is alpha Y, and then we need to do superposition of this with the derivative Y dot. Initially Y dot is positive. So initially it's positive, say something like this. And then the derivative, you can see the slope is sort of first increases and then decreases until it hits the first peak. It becomes 0. Okay, so this is, let's say, this is the location of the first peak. It's going to be something like this. And then it oscillates. There are negative slope. So the derivative with Y dot will have negative value. And it may look something like this. Okay? So that's the superposition between these two. The exact shape, you can see, obviously will depend on this. This is already defined if this is given. This one, the shape, will depend on alpha. If alpha is super large, right? If the scale of this effect is super large, then maybe the effect of the Y dot won't matter that much. However, let's say if alpha, let's consider two cases. Alpha, let's do positive and negative. So if alpha is, let's do positive. If alpha is positive, then that means my 0 location is S equal to negative alpha. So my plot is going to look like this. Pole 0 plot. Two complex conjugate poles. And location, actually, we can also know. Okay, so these are the complex conjugate poles. And then the 0 location is negative alpha. Alpha is larger than 0 if alpha, let's say it's here. If alpha is larger than 0, then you can see the effect will be a scaled version of y. Y tilde t shape still similar to yt. So if you add these two together and alpha is larger than 0, let's try to draw this. Initially, it's gonna make the signal to go faster, increase faster, right? So it's gonna be a little bit faster increase in the beginning, and then somewhere in the middle point, the speed of the additional effect of accelerated increase will start to decrease, and then oscillation. So I exaggerated a little bit about the initial speed up of the increase to give you the idea. The response will look similar to the original. So this is the 0 is on the left half plane. It is a stable 0. Interesting thing will happen if it is an unstable 0. Let's try to visualize. Pole 0 location, let's say the poles are this, and alpha is somewhere here. So alpha is less than 0, and this is negative alpha. That's the location of the 0. So that means alpha is less than 0. Alpha y will be here. It will be flipped. This is the case alpha equal to negative 1. So you have a mirror image of the y signal. And in this case, you can see the response will look like it's going to be this, and then the y dot effect is going to, you can see initially it's less than 0. If y dot, this initial positive value, it can have the potential to make it to go in the other direction. So you have potentially this is negative alpha, and then the response can potentially be, so this one, add on top of this one, it can have this initial curve to be going to the other direction of the real axis. So it may look something like this. Okay, so I will emphasize this part. The steady state value is the same, you guys see, right? Because y dot at the steady state is 0. So they're going to go to the same place, but initially you can have this interesting sort of undershoot in the other direction of the curve. So this would be negative alpha plus y dot. This is the example of alpha equal to negative 1. So you have this initial undershoot instead of, so we call this is overshoot. You go beyond the steady state value. And then undershoot is if you go the other direction compared to your steady state value. Obviously, this is not as good as this. This one, the 0 doesn't change the shape that much, but this one, it changes its shape completely at the beginning. What that means in practice is, let's say a motor, position motor. You apply a input and you want the position of the motor to rotate to 10 degrees. But if you have a unstable 0, it's going to rotate in the other direction first and then go to the direction that you want. So unstable zeros is not great in that sense.